Okay, it should start happening. Yeah, okay. So as I was saying, the system catalog, which will actually say that here, if you are talking about some relation, say uh, select star from R, then you need to know where all R exists and in which way. Uh, I have the transparencies which are getting shared. Can you see that? I'm writing on
So your screen is not visible.
my screen is not visible. Oh my. Okay, let me share it again. Is it visible now?
Yes, sir.
Yes, sir.
Okay, perfect. Thank you. Yeah, so therefore, there is a user who will ask a query to this distributed DBMS layer, and then the distributed DBMS layer will access these three systems and get the result. So, for example, if you say select star from R, part of R could be here, part of R could be here, and here, then there will be three queries that are generated, and then you get the result, you combine it, and then you get back to the user. So, this is the layer that you are going to build, right? So, starting from taking a SQL query, coming up with what are known as local queries at these levels, and then getting the result and combining. So you are actually doing a lot of inter-system communication. So you are going to write function calls which will send these SQL statements to another system. And there is a receiver for these function calls. And then that receiver is going to process that particular instruction that you have called, and then go and access something from the data, package that data into some data structure or some file, and then or a CSV file, and then ship that across to this distributed DBMS layer. And once the distributed DBMS layer gets all these shipped data, then it knows what they are, and then it automatically initiates the code to combine all this data and then get the final result and give it to the end user. So it looks conceptually simple, but to do it for any kind of a query and any access, that's where the challenge occurs. And that's what you are going to learn. So you are going to learn how to take a query that has data across multiple systems and how you are going to get the result. So the aim is to build this functionality layer. We are going to, I've asked us institute to provide systems that are there. So I'm getting 6 systems from the institute, which you will use for this project. And you will use 3 sites. 3 is a good number of sites. We will support fragmentation transparency. I'll let you know what this means shortly, either today or next class. There are 4 phases in the project. There will be multiple demo sessions. The databases are fixed, like MySQL and so on. The coding can be done in any programming language that you want. The project can be done as a single user or a single student or group of maximum 2 students. So one more slide about the project, and then you can ask me questions. So by January 18th, you need to do the system catalog design and implementation. I'll put up the note on that. Then by February 18, the query decomposer and data localizer So what it so this will tell you that a given relation R is R1, R2, R3 at this site, at this site, and this site. That's what this information will provide you. This will say that given a query on R, it is going to divide into query on R1 plus query on R2 plus query on R3. Note that these are all conceptual operations which are combining operations. So they are not additions, but combining operations which will give you the thing. Then once you know that these are the things, then you have the query optimizer, which will tell you that how to execute these queries efficiently. And then there is the updates that you need to provide the support for. And these are the deadlines so that you can work on it. Um, so there are few one more slide, and then I'll take questions from you all. Uh, so the slide is uh, that don't start just 1 2 days before deadline. There is so much of coding and so many things that can go wrong that if you start between 1 or 2 days before deadline, most likely you will not do well. System catalog is very important. So an inappropriate design may give rise to a lot of issues in subsequent phases. You need to work incrementally and continuously. But the good thing that I have realized from teaching this course earlier is that when you finish the project, you come out as a better person. You have achieved something which you thought that was fairly impossible to do. This is like a kid building a toy aircraft, and that flies. You know how Boeing aircraft is there. It's so very complicated, but building a small aircraft that can fly on its own, with your effort, that's the kind of exercise that we are doing here, where you are building a small system that can take data from multiple sources and provide the result to the end user. And you can see the amount of effort that goes into doing that, and what are the design choices, what are the coding choices that you do. And here we are not looking at we are looking at a workable system. We are not looking at a production ready system. So therefore there will be a lot of temptation on your part to make things perfect and to make coding optimal and so on. Try to resist that, make sure that it works first, and then if it is really, really critical that something is really causing problems, don't then only you change it. Otherwise, any change that you make, you have to change a lot of other code related to it. So therefore, be extremely, make sure that you can get things working, then working very, very well. Okay, you have a lot of time later on to further develop it. Um, so any questions as of now, be free to just unmute yourselves and ask questions, and then on the project, on whatever I have said about the course till now. No questions? So we will have 1 hour of TA-ship per week, and also I'll use some of these classes for actually project work in this. So therefore, you will do some amount of project work in regular class as a group. You will be working on it, and so that there is periodically there is significant progress that happens. I teach something and then I'll ask you to do that with respect to the project. So therefore, there will be some amount of schedule that we will maintain. Okay. Then there is this slide about academic honesty. All work design and code must be original. Sharing of code is between the groups is not allowed. Collaboration is also not allowed. If you are using something from the net, then you give us the references. Though I doubt there is much that is there related to this project. Uh, the both members of the group should work if it is a group project. Separate viva may be taken. Any violation of above results in assigning a lower grade or direct F grade. See, one thing that I feel is that almost all of you are in the same boat. All of you are attending the same lectures. All of you are picking up whatever you are picking up based on what I teach and what you read, right? And anybody who is dishonest is actually getting a unfair advantage because other students have actually put in a lot of effort in the course. They have done it alone and they have taken the pains to do it. And somebody else getting that advantage without putting in that much effort and understanding is not right. So that's why I tend to be very strict with respect to academic honesty. And I want to give a lot of benefit to the people who work hard and who learn things on their own. Even if they don't do it completely, but then if they do it on their own, they have learned a lot more than somebody who has just taken it from somebody else. In case you have any doubt about whatever you are doing, whether it will constitute cheating or not, send me an email, and I will give you an explicit email saying that yes, this is allowed, but this is not allowed. You know, so that's the note on academic honesty. Okay. Any other questions at this time? Fine. So we'll start with the basic material of the course. So the whole, so there was this in early days. There used to be a single computer, as you must have realized. Thomas Watson said that the whole world would need about 5 computers to all its processors, and now we have IoT devices, each of which is a kind of a small computer. If you look at 1950s technology, and there are trillions of such devices around in the world and will soon be there. So therefore, this notion of single computer or a mainframe is gone. There is no more such notion. So if you look at the modern GPUs, CPUs, and all that, you have either uh, within the box mini computers, or within a motherboard mini CPUs, right? So there is this, a CPU exists almost everywhere. What does a CPU do? It has two inputs of data, and then it has an output, and it does some processing. It has some registers, and the whole gamut of getting the results. So that processing unit, which is a small CPU, that is prevalent in many, almost everything that you touch. This pencil onwards that you touch has a CPU in it, right? So therefore, and they are heterogeneous. There are different kinds for special, very special purpose to general purpose. The only thing that distributed computing does is that it says that these set of processing units are part of a network. They are connected, right? So therefore, this is treated as kind of a one unit of distributed computing. It is treated as one unit of distributed computing, and that's what this is. And what gets distributed here, the processing logic can get distributed, You are doing sorting across all of them, or you are executing the same code on all of them. For example, select some salary from employee. You are executing it in all the nodes, right? The function can be distributed. The GUI, this one might be connected to the end users and has a very fantastic GUI and is basically handling the front end. This one could be connected to a large data sources, and it is a very powerful machine that is doing OLAP kind of queries, right? The data could be distributed. Right. Data could be actually taken and put in multiple places, or data can actually be generated at multiple places. So, for example, sales data in Hyderabad could be generated in Hyderabad, stored in Hyderabad. Sales data in Agra can be generated in Agra and stored in Agra. So the data itself is generated in a distributed fashion. The control can be distributed, like who does what. Sometimes this node can become the main node, which is telling other nodes what to do, or these two nodes become the main nodes, which are telling other nodes what to do. So the control can be distributed. So therefore, in a distributed computing environment, all these four things are distributed. So the basic thing that we in per se look at from the point of view of distributed computing is uh, is that we are not per se looking at the distributed systems programming aspects, like maintaining mutual exclusion in a distributed environment, or managing the distributed directory, or and looking at consistency across protocols across that. Those aspects are hidden from us. So when we say that we are doing something, it is on top of that. That functionality is below our environment, and we take that for granted. Similarly, as we take CPU scheduling as granted when we do database systems processing, here we take this distributed computing or distributed system infrastructure as granted. So what we say is, if I send a RPC to remote procedural call to another site, I expect the other site to respond within certain time, and there are no failures. And whatever data that I get from that site is correct. And during transmission, nothing goes wrong, right? So these kinds of things, we basically assume. And if I can broadcast my thing to multiple sites or to a single site, those kinds of functionality, I assume that the underlying system is going to provide. Okay. Any questions? As I said, feel free to ask anytime. You know. So why distribute at all? It's more reliable and more responsible. One interesting reason why you distribute is, especially from the data point of view, is that suppose if I have 1 petabyte database, right? Now, if I want to store it on a single system, I would need multiple hard disks to store it. And second thing is, if I'm processing anything on that, I need to, even if I do B trees or B plus trees and all that, there is a significant number of accesses that I would want. And for most of the queries, I won't be accessing the whole petabyte database. I'll be accessing only a part of it. So therefore, having to churn out all this unrelated data for a long duration to find the relevant data is a big overhead, right? So therefore, by actually partitioning it into across various systems and knowing what is there in these systems would help me to go to a corresponding system and access the data, and that will be a smaller piece of data, and my systems would work efficiently. And second thing is many applications are inherently distributed. So if you look at Facebook, or even if you look at Amazon, right, or Flipkart, or let's say Best Buy, Big Bazaar, Big Basket, and things kind of like they many of the transactions are actually occur in a few major cities, right? So and then many small towns. So Hyderabad, Bangalore, Mumbai, Kolkata, Delhi, right? They occur there, and the data can be stored there. And because you get a lot of local knowledge, and your data will not be influenced by data from Hyderabad. So if I have Delhi and then I find that Delhi people are buying certain things, I don't want them to be influenced by what Hyderabad people are buying. And if I mix these two data sets, right? So therefore, locally the data is distributed, and I want to store it in a distributed fashion for local data processing and divide and conquer, right? So if I'm doing sorting, instead of sorting 1 petabyte database, it's faster to sort, 100, 1 terabyte or 10 terabyte databases. So it's much faster to do it in a distributed aspect. And there is also an economic thing. Buying a huge system is very costly. And whereas buying a off-the-shelf, say for example, Apple iMac Mini, I can buy 100 iPad Minis, then one system that can manage 1 petabyte database. And I can include this 100 and get my processing done. It is much cheaper, more fault tolerant. I can each replace one mini with another mini and so on. And the development effort is also is simpler because your code is distributed. What each distributed piece of code is doing is very clean. And and there is a nice workflow process that is maintained for you to for these things to run. So therefore, in that context, this whole environment is cost effective and development effort effective. So if you look at database systems actually have this logical and physical, especially relational databases, right? The way we studied them and they are built is the logical and physical. So I say, get me the names of all employees whose salary is greater than 50,000, right? And the system does that. I don't have to know where the relational database is, how it is stored, how this query is going to get processed, and so on, right? And even the physical independence, I can move the data from one disk to another disk. I can change the way I'm storing the data from one page design to another page design, and system would still run. So therefore, you are transparent to the how the data is managed by the DBMS, right? And so typically, if you look at a file system, that is not case because your data description is there in all the programs, and you need to explicitly comprehend this. So if this file format changes, then all these codes have to be changed, right? If I add some attributes here, I need to change. If I move the data from this disk to another disk, the whole thing has to be, the code has to be changed, right? Whereas here, this DBMS actually does this management. So it does this file management by itself, right? So it takes up it takes up the load of managing all these files, managing all this A by itself. So therefore, end users don't have to see A at all, and so therefore A is transparent to end users. All that is visible to the end users is this interface that is there. the interface that is there, and so on. So therefore, a good comparison is between Kirana store in your neighborhood and a Freshette or a More or any of these major grocery stores like Vijeta. So in Kirana store, you ask the person, right? And you say, get me half kg of tur dal. He goes inside, he packs it, and he gives it to you. But you have no direct access. You cannot know where it is. You don't have to do anything, right? And nothing is. So therefore, you are transparent to how the Kirana store owner actually gets that for you, right? Whereas if you go to the one of these Vijetas, there might be four open baskets of open drums of tur dal or whatever, and then you can check that, look at it, put it in the bag, weigh it, get a sticker on it saying that how much it costs, and then go and do it. So you have to do the whole process by yourselves, like a self-service kind of a thing, right? So now you can see that if that drum was moved from one place to another place, then you have to go around searching for it and then do it, right? And if the tur dal has some dirt or some other things, you have to remove them and all that. You have to process it and then you have to get that to you, right? So therefore, if without transparency, you need to be more aware of the environment. You need to be more aware of what is where. You need to be more aware of the processing. That first I need to put it in a bag, then I need to take it to another person, get it weighed, then I need to get that sticker on that, then I need to do other things, right? So therefore, I need to be aware of the process that is to be followed. Whereas with transparency, I don't have to know anything. I just say, get me half kg tur dal, and that person brings it to me. I pay for it, right? So therefore, how much of detail that you need to know is having transparency or no transparency. Okay, so database systems essentially provide this transparency. So a distributed DVMS is a union of uh, two diametrically opposed approaches to data processing. One is the database systems that is trying to put everything together, provides transparency, hides things from you, and gives you a access control where you get to see only what you need and not everything. So you don't even know what the whole database contains, right? And computer networking, which was actually a facilitator for distributed computing, like put everything away, don't use one system, use multiple systems. You can work from home with distributed computing technologies. You can access systems from various sources, from various devices. And all this is made possible from computer networking. If there was no computer networking, the whole world would have not seen Facebook or Twitter or any of these World Wide Web, right? So therefore, it essentially provided this ability to make multiple computers to work in unison to address a particular user's needs, right? And it can be a narrow user need or it can be a broad user need. So IRC, or Book My Show, unfortunately, there are no shows, but right. So if you look at it, there are multiple systems that are involved in these. So there is a front end, which could be your mobile, then you connect a web server, which connects to a transaction manager server, which connects to a database system, which might be accessing something, and then you get back your information and your system, right? So therefore, you are actually doing a very narrow, but you are connecting many systems underneath it. So it's and you can also think of a multiple broad-based environment system. Say, for example, you have something like Amazon. I'm giving this example in the following sense. So I may get from the Amazon catalog database, I'll get some information which shows me, a computer mouse. Then I access another things which gives me reviews. I access third things which gives me a comparative list of other products. I access the fourth thing which tells me what kind of sales are there and packages. Then I access the fifth thing where I can go outside this system to some other system like a web browser and do further analysis of that, right? So therefore there are so like the product manufacturer website, right? Where I can get additional details about the product. So it's a very broad environment. And even within the same notion of an Amazon, which could be, or a Flipkart, which could be a single purpose user interaction, I might be accessing A, B, C, D, E, and F separate systems, and each one of them is a multi-computer system, right? Is a distributed system which does multiple things, and I am accessing this breadth-wise so many systems for one unique purpose of buying a computer mouse, right? And I'm accessing all of them. I'm able to see that, and I'm able to decide. And then finally, when I decide to buy it, again, I'll hit multiple systems. One for paying the thing, one for the delivery, and one for some feedback and things like that, right? So therefore, you may hit about 200 computer systems in a shopping cycle, individual computer systems in a shopping cycle. And all that happens in reasonably good time without too much of latency. Sometimes you see some latency there, but you don't actually know what these systems are, right? So therefore, in some sense, both of these problems, that is the Book My Show or IRCTC kind of a environment, and this broad-based environment, which is Amazon. I can even increase this example to something like a socio-economic environment of getting data from some source, theory from another place, something else from some other place, and building a large system, right? So therefore, I can even do cross environment, cross a larger purpose, right? So for example, another simple example is a holiday, right? So you want a train or plane tickets. You want hotel environment. You want sightseeing reservations. You want dining reservations, and so on. And all these are multiple tasks that need to be performed, and multiple different functionalities that needs to be performed, and each of which is totally different, right? So these kind of environments could touch even 500 different systems in one total action place. And here you can say that if I don't get a good hotel price, then I won't fly on these dates, right? So there is a iteration that happens, right? And then if I don't get a reservation to see this tour, I won't be staying on those dates. So there is a musical concert, and I want to be able to attend that musical concert and get a ticket If I get tickets, then I want the hotel room to be reasonable. If I get the hotel room, then I want the flight tickets to be reasonable. So there is a lot of churn that happens in this decision making, and this whole process could, which is a planning a holiday, is a totally diverse. So this could be make my trip. This could be TripAdvisor. This could be sightseeing. Could be tourist state agency. Dining could be Zomato or some such thing. So therefore, I have a totally independent platforms which I have, and I am accessing this. So therefore, this the underlying theme is purpose-driven solutions, which require distributed data, right? So you have purpose-driven solutions. You have a purpose of planning a holiday. You access the whole systems, which are independent systems. You have a purpose of buying a simple mouse, and the system that you are accessing actually handles multiple data systems in some sense. You have a purpose of just buying a simple movie ticket, and that goes to a vertical deep set of systems, and each of them are different systems connected by network. So therefore, network is very prevalent for communication, data transfer, control in getting these things done, right? So any questions on this slide? So give me a +1 if you're awake and listening. Yeah. Yeah. So yeah, thanks. I got it. Yeah. So, so this though I have presented it in this manner, many of these things will not be doing in this course. Okay, I want to say that also. But what I wanted to say is the scope of what distributed data, which is implicitly there, is what I wanted to present. That and the tight interconnection of computer networks to the processing of data is very much there. Even if it is single database, even if it is simple book my show kind of a thing, you might hit multiple systems, and that is not distributed database systems. Amazon thing can be of a loosely coupled distributed database system. The holiday planning is a federated, that is different kinds of databases, distributed data systems. What we are looking at is more of a homogeneous single layer kind of a system. So, so if you look at the database systems and computer network technologies, promotes a mode of work that goes against centralization effort, right? So it says that why do you want to have one single mainframe? You know, why do you want one single system? Right? So you are better off by having multiple computer systems. But when you talk about database technology, you start thinking about saying that okay, I have all my database in one disk. So you start thinking that it is centralized. So in a data systems course, that's what we say, that we have a B plus tree, we have the page design, we have the transactions happening. When I'm doing a SQL query and I'm performing join operations, I'm taking pages from a single system and then I'm bringing it into the environment and so on, right? So therefore, there is some kind of a notion of one single system and all data residing it. But the most important objective um, uh, of database is integration and not centralization, right? So it is not centralization, it is integration. So integration does not imply centralization. So if you look at this Amazon shopping experience, the shopping experience treats the whatever you see on Amazon site or Flipkart site, that is the experience, right? That is the data that you are getting. You are getting the reviews, you are getting the product details, you are getting the pricing information, you are getting the comparative recommendations. That is the integration of data that you are getting. And there is no central databases that has all of that, right? So therefore, integration does not necessarily imply centralization, and centralization need not imply the data is integrated. I can have multiple files which are separated, and then we have. So if you look at distributed databases, it is integration without centralization. So you are actually saying that I'm treating a database as a one single schema or a connected relational database schema, but none of them are by themselves are a single system, right? It is not a stored in a single system, right? So therefore, our focus is on how to support this integration, right? So our focus is on assuming that there is this integration. How do I support this integration without centralization? I know my data is in multiple servers. I know my data is related in some manner. So given a SQL query, how do I get data from this and get it? Um, Again, I'm going to digress a little bit here and go back to these examples. Is that there is actually a process here, right? So if you take this Amazon example with this A, B, C, and D kind of environments here, right? The this web page that I'm seeing, right, which has all this information, that web page is the integration page. It's a loosely coupled integration page. So for example, sometimes it says that price not available, right? It implies that in the corresponding database about the price of that product, there isn't enough data there to data for about the price. Sometimes it says the product description is not available, right? So that means that the corresponding database for products in information is not available. So the integration happens in the design of this web page. So if you are using JavaScript or you are using something, then for each component of this particular web page, you are running a piece of code. And that piece of code actually touches some catalog, some database, some SQL querying, some processing, and extracts the data from it and presents it there. So therefore, the web page design, the design and the code of that particular web page is the integration. And there it is hard-coded integration. No, yeah, there will be some amount saying that access this relational database or access this, but even that has to be specified. What you need to access has to be specified, right? So that's the kind of integration that you see. And here, if you are looking at book my show kind of a environment, the integration is actually on that app that you have. So you first select the movie, then you select the date, then you do that. So you are drilling down into that actually what you want to book, and then each time you are accessing some data and across the network and getting it, right? So therefore, this is the breadth, that is the depth, and they both have very interesting ideas. So this notion of integration, um, how much of this integration is has to be coded by you? How much of it has to be quote unquote hard coded? How much of it has to be incorporated in your software system that supports this? Is all very interesting design choices. So a distributed database is a collection of multiple logically interrelated databases distributed over a computer network, right? So the key here is the following: multiple, not one, greater than one, logically interrelated, single ER model, right? So across all these databases, there is a single ER model. Okay, logically single ER model. Distributed, that means there are actually separate databases, right? And they are connected by a computer network. They are not on a single server. They are not on a GPU, CPU, multiprocessor kind of environment. They are not necessarily in the same building or in the same room. Okay. So a distributed database management system is a software that permits the management of distributed databases and makes distribution transparent to the end user. Right. So what it does is it provides you with the ability to access this logically interrelated multiple databases as a single unit, and you as an end user need not even know what exactly these multiple databases are, where the data is stored, and how it is right. Uh, and One second, I'm just trying to, yeah, and um, uh, how it is processed, right? So everything is not known to you. So from the end user point of view, you don't even know whether you are accessing a distributed database or a centralized database. So your front end remains the same. You still say select star from R. Whether R is a single relation in a single system or whether R is distributed across 500 computers, it doesn't matter to you. The distributed DBMS layer will get the data from all these sources and give it to you. So therefore, that's what this making this distribution transparent means. So that is what is there. So database technology provides integration. Distributed computing is supported by computer networks, and a distributed DBMS provides integration without centralization, right? And this is the goal. So this is where we go with it. Um, uh, the interesting part in this is uh, how to achieve it, right? And There are a lot of things um, uh, are are pretty much open when we start looking at this distributed database systems, right? What is open here is what kind of database technology do we have? Do I have relational? Do we have graph databases? Do I have object-oriented databases like O2 and so on? Do I have something else like network databases? Do I have flat files which are managed by a layer, a document repository, a spatial or data streaming and environment, that is open. Database technology that we have is open. The computer networks, what kind of distributed computing infrastructure do we have? Do I have only unicast? Do I have broadcast? Do I treat separate clients and separate servers? Am I, am I doing push-based or pull-based environments? All that is again open, right? Are there certain systems which are multiprocessor systems, which are with multiple disks that can, which shade everything or shade nothing kind of environment that provides certain functionality for me to execute certain things? Is there a GPU-based system that does something very efficiently? What I have is again open. So what is my distributed database system? It just says that I will provide you with a front end kind of a thing, such that you think this both database technology that is there and the computer networks technology which is there, they both are hidden from you. All you see is what I show you. All you see is what I can provide you. And within this, you can do all your processing. I can have a Amazon kind of environment. I can have a regular distributed database kind of environment where I can do select star from R kind of environment. And only thing that differs is the layer that this distributed database system has. That's the only thing that differs. Okay, and how thick or how lean it is, what functionality it provides, what all can it do, how much of it can it do, all these are open questions. Any questions, concerns about this um, uh, topic till now? Any questions? Okay. So so here is the distributed, geographically distributed data centers kind of a environment, right? They are geographically distributed. This is pretty much for the case with many of the Facebooks and Google and all that. And even companies have it. So for example, IBM would have multiple data centers for their own processing. Microsoft would have that. Many of the large organizations, which sell billions, Amazon, for example, would have multiple data centers where they do this processing. So therefore, there is this prevalence of uh, uh, high latency, geographically distributed data. So therefore, it takes about, if you do ping from here to US, it may take about 200 milliseconds. So that is the kind of latency that we are looking at, in processing and so on. So therefore, if I have to send 1 megabyte of data from one place to another place, it will take a certain number of seconds to get the data and then process it. Okay, so here is a kind of a question that you need to ask. Why is time sharing computer system not a distributed DBMS? Answers? Any answer? Yeah. Yeah, Karthik, go ahead.
So they're part of the same system.
Right.
Everything.
So there is no data that is there. You can execute multiple queries at the same time, and they get processed one after another in some order, right? The way CPU decides, but it doesn't have data. What about a loosely coupled multiprocessor system?
Processor is independent.
The processors are independent, and they may have within the motherboard or within the system network connectivity, right? Right. So they are connected multiply, right? And but that doesn't make it a distributed, geographically distributed. You are not going away from this system to another system through a computer network. And whatever you do is within one box. You are not going out of a box to another box, right? A database systems which resides at nodes of a network of computers. Um, but unless the data is integrated and interrelated, it is still a set of centralized databases. It is not a distributed database. Okay, so these are, we'll talk about this little bit shortly. So if you look at a distributed database environment, you have a communication network, you have sites like Paris, San Francisco, Waterloo, and Boston. And in each of these places, you have various relations. So here you have Paris employees, Boston employees, Paris projects, Boston projects. And then here you have Boston employees, Paris employees, and here Paris projects, and here San Francisco projects, and so on. So therefore, if I want to say, do this, select count star from employee, right? So this is a very standard query, right? And what would happen? I can, if I were to get it, I need to get employee count from here, employee count from here, and I can get these two counts from here, right? So I don't even have to access Boston, because both Paris and Boston are there in Paris. And similarly, I don't have to access Paris if I access Boston, right? So therefore, executing this select count star from employee is can be done by accessing these databases, and they are all interrelated. So the same employee table, for example, select where city is equal to Paris, or city is equal to Boston, or San Francisco, or Waterloo, they all will give you the different tables which are stored at different sites. And then doing a union of this would give you the final result, right? So therefore, this is essentially a interrelated database. If you look at it, it has a single ER model, employee works on projects, right? Kind of a ER model, and the data is actually stored in multiple sites, right? Any questions on this? Okay, so the big picture is here from the end user point of view, right? You are seeing the data as a global database. So you are seeing, as we show here, right? You are seeing this employee works on project. This is what you are seeing. You are not seeing at here. This is what you are seeing. You are not seeing Paris employees or Boston employees or San Francisco employees and so on, but you are actually seeing only employees. And this is what is shown to the end user. Now the end user will say select const star from employee, right? Now this distributed DBMS then decides, okay, I want to go to San Francisco, I have to go to Waterloo, or I can, and then I need to go either Boston or Paris, right? I'll go to Boston or Paris, and then you decide, and then, or you may go to both Boston and Paris and wait for whichever one gives you the results first, and then use that result, right? So this thing where you have to go and how you have to do this is decided by this distributed DBMS layer. So this distributed DBMS layer, given a query like select count star from employee, decides, okay, I need to know, I need to go to San Francisco, I need to go to Waterloo database, and I can go to Boston or Paris database, right? And then I need to get those values, and then I need to combine the result. So this layer that you are doing, you are the one who is going to build this layer. You are the one who is going to say that, okay, employee is not one single table. Employee is actually divided into Boston employees, Waterloo employees, San Francisco employees, and Paris employees. And therefore, if I want to do anything on employees, I need to access these four. And depending upon that, I need to go and get those data. So that is known as data localization. That is figuring out that the query select const star from R actually accesses Boston, Waterloo, and San Francisco is what you are going to decide. Now, if I put, so for example, if I put Boston employees here and Waterloo employees here, right? Then I just need to access San Francisco and Paris because those are the only two things that are that have this, right? They cover the entire scope of the relations. So therefore, when I change things in terms of what I am putting where, automatically, given that query, will go to the new configuration of my database and access that and give it to you, right? And that is done dynamically. It is done at the time of query. Once the query comes, your distributed DBMS is not going to hard code and say that you have to go to these places. It is going to go and look at your system catalog, find out what are places this employee data is, pick that up, reformulate the queries into those queries, efficiently execute those queries, get the results, and give it back to you, right? So that much amount of hard work has to be done by this distributed DBMS, and that is part of that 5,000 lines of code that you are going to write, right? So you are going to build this kind of a infrastructure, which is generic infrastructure, not hard-coded infrastructure, and it is going to do the whole processing. And of course, you have to do it correctly, right? If you get wrong results, if you miss out San Francisco results, or if you miss out Boston results, then people are not going to buy your system, right? So therefore, you need to do it pretty much correctly. Okay. So then, what are the implicit assumptions here, and why these assumptions are necessary? Data is stored at a number of sites, right? And each site consists of a kind of a single processor, single computer, right? Otherwise, it is not a distributed. You are not going across computer network. So data has to be on separate machines through a computer network. So it is not a multiprocessor system, right? Though one of them can be a multiprocessor system, but as long as that is hidden from me, it's fine with me, right? But I don't want my whole complete system to be a multiprocessor system. there is one line of work in databases which is known as parallel database systems, and there is significant amount of work how in a shared nothing or shared everything kind of environment. Shared nothing is the memory is not shared among these multiple processors. Data is not shared among these multiple processors. Then how do you process queries? And in shared everything is memory is shared, data is shared, and then how do you process? So there's whole area of line of work which is parallel databases that covers that. And distributed database is a database. It is not a collection of files. Okay. So therefore, you have a kind of a DBMS at each site. Okay, so therefore, you not only you have a database, you have a small DBMS on top of it, and you are actually talking to these DBMSs. So there is some local processing that is done, and the DBMS manages the local data, and you do a global distributed environment. And we will stick to relational data model because they are much easier to handle, and many of the concepts are much more easier to work with a relational database, easier to understand and perform. Whereas if I move away from relational databases, the code complexity explodes. The comprehension complexity will explode. And a generic such environment is a lot more complicated. So a distributed DBMS is a full-fledged database management system. It is not a remote file systems. It's not like Dropbox kind of a thing, right? It is not a transaction processing system where thousands of users are going to IRCTC and buying their tickets. It's not that kind of a system. It is actually a fairly large ER model with data that is spread across multiple sites. So any questions at this point of time? Anything that you would like to ask? Okay.
Could you talk?
So yeah, go
Me.
ahead, please.
Could you talk through the system catalog? Like you said, system catalog would manage. System catalog is used by the distributed data system while
Right.
fetching the data.
Right.
So system catalog could be because I have to distribute the data, the big data, to all those systems. So that information is kept in the system catalog or anything else.
Yeah, so a quick answer, a system catalog, the system catalog will tell you the mapping, right? Which database is there where, right? And it provides, so if you see this diagram, this A will correspond to relations, employee, project, and works on these three relations, right? And this employee is split into Boston employees and so on. The project could be split, works on could be split across multiple sites, right? So the mapping between E to its each component of P to each component and where they are stored is what is there in the system catalog. The way you are going to build this solution is to first you are going to design how you are going to store this system catalog in a relational database, and you are going to store this system catalog in all the sites. That is, you are going to replicate it in all the sites. So therefore, the query can go to any of these sites. When the query goes to any of these sites, each of this layer is present in each of these sites. So let me erase this and explain it slightly better. So so there are two parts here. This is A, and there is a system catalog, and with a set of functions, right? It will say that give me number of fragments, which that's what we call fragments of relation R. Then the system catalog will say R is actually divided into R1, R2, R3, and R4, right? There are 4 fragments of R. Then if I say give me for S, it will come back and say S is divided into S1, S2, S3, right? So this functionality is provided on system catalog. So the system catalog, the functions and the system catalog, which is a database, as one single unit, right, is, say, let me call it as B, is there in each of the sites. And this distributed DBMS layer A is also there in each of these sites. And this layer A is the one which is talking to the end users. So the end users can use SQL and say, select star from R, right? And that comes to this A, right? Now this A will use this B and then does the processing with itself and generates queries like, say, select star from R1, select star from R2, and so on, and ships them to various sites, gets the data, and does the processing. Okay, so designing of what goes into this system catalog, what functions you need to provide on this system catalog is the design exercise that you have to do. Does that answer your question?
Sir, so the system
Yes, sir.
catalog can be dynamic?
No, in our environment, we'll keep it as static. We'll maintain that our schema is fixed and our fragmentation is fixed. So therefore, it is static.
Okay, sir.
Otherwise, it becomes too complicated.
Yes, sir.
Any other questions? Right. So this is what the implicit assumptions in a distributed DBMS are. So the early distribution was what I showed you. Is a communication network and actual. So these are actual relational database management system. This could be Oracle. This could be Sybase. This could be SQL Server. This could be DB2, things like that, or all of them can be same version of Oracle and so on, and they are managing the systems. Then you have another environment where you have client and server, but this is this still works for us where you have this A and B as a distributed DBMS. If they are there in A and B at every place, then it will work and client can access any query to any of these environments. Right, so you want those A, the system B, the system catalog, and A, the distributed DBMS layer in all of them. The third architecture is that this can be my. So let me give you a simpler example. This can be our IT department. Income tax department, which is managing our income tax and other things. And this can be a bank, and this can have the credit card information. Say, what expenses have you made on your credit card? And this can be the enforcement directorate, right? So the enforcement directorate can access through your PAN card, right? What your income is, how much taxes have you paid, what kind of things that are getting. And from credit card, they can, banking credit card, they can say that, okay, how much of foreign currency have you spent? How many plane tickets have you bought? What is your monthly expense and so on? And then they can say that, okay, your salary and your expenses are matching. So therefore you are safe and you are doing well within your means. Whereas if your salary is much, much less than your expenses, then they will say the difference, where are you getting from, right? So therefore here, this is a layer which is built by Enforcement Directorate to connect to the database, which is income tax database, which could be a separate database, separate sensitive database, and the income tax database might only say only this amount of data can be exported, and there are things like that. And same thing with credit card database environment and so on. And so here the schema, that is what is needed, is here. So the integration is done by this layer. So it is somewhat similar to that Amazon example that I have shown, the web page. That kind of integration, loosely coupled integration, happens in this multi-database layer. And so you don't even, there is no, so the system catalog in this case would only say that how to access these local databases, and it can also, oops. Yeah. So in this case, the system catalog might even only say that you can only run these remote procedural function calls, right? Remote procedural function calls, or you can only run these SQL queries on each of these databases, get the result, and go on. Enterprise. E is enterprise. A is what? Application layer. You can speak up in some sense. Yeah. Yeah. So therefore, yeah, you can call that as that in some sense.
So I'm trying to understand, because we're trying to build an integration layer, which is like an intermediate layer. Can you hear me?
Yeah, I can hear you. Yeah, we can hear you. Yeah.
We're trying to build an integration layer between front-end and the back-end systems, like through the DDD. Can we call this as integration layer, which calls multiple downstream systems, right?
Yes, you can call it, and we'll see how that kind of a solution works. Little bit. Okay. Yeah. But what we do in this course is more of a traditional relational database. And the another thing that we have is the cloud computing, which has become very common, right? And there again, you have there are providers with different kind of functionality and service providers, the app server, the various service other providers, and the databases, and you access it from there. So the basic here is everything is in Flex, right? So there is a infrastructure company that manages all of these. The apps, how many apps do you want? What performance do you want? How many people are accessing your system? Everything is managed by some other company. And all you are saying in this company is, in this environment is, this is my functionality that I want to support. I have these databases which are disparate, which are different, which have this data, and then I have this. So your distributed database management system layer, which we call as A, could be a server here, a app server. And so therefore, this A would reside here. From your mobile, you are calling this A, and A is actually accessing these databases, generating, combining all this data and providing it to you, right? So therefore, in that context, it becomes a service that is provided. It actually becomes an API that you can use. So therefore, your the functionality that is provided by this distributed database management system layer can be a set of APIs which people can access to access the database. Okay. So any other questions in today's class and overall environment of this course, the conduct, the grading, anything that you want to ask? Okay, this is a good time to end today's class, because next class we can start with some other aspect. If you use the course forum to ask for any questions, set up your teammates for the course. If you are doing alone, let us know. And Thursday I will meet you. And in the meantime, I'll tell you about the tutorial hour or the lab hour for that, and also the other aspects. We have a TA assigned, Freya Mehta. I'll put her up on the Moodle for you to contact her. And that's it. Any other questions? If there are no questions, we'll end the class. No? Also, let me know if I'm going too fast, too slow, or anything.
Sir, what is not a DDBS in that slide?
Okay. Here, right?
The third point, I'm not entirely sure why it's not.
Okay, so right. So this is a remote procedural, remote access to the database. So it's like the Aadhaar card kind of a thing, right? And there are multiple users accessing it from remotely. This is not a distributed DBMS.
Okay.
Okay, so a single database which is accessed from remotely.
Okay. Okay.
Yeah. Yeah. Any other questions? Okay. If not, then thank you very much for attending today's class. And I will again see you on Thursday morning. Okay, bye.